2.1 through 2.3. Okay, so first we should unpack what all of that means. So we often ignore the words like linear and one variable because when we start learning how to solve equations, we only solve linear equations in one variable, so it seems like that's the only technique that we need. As we progress, we will be solving different types of equations other than linear equations. So it's important that we think about how to recognize a linear equation so that we can use the right techniques. So that's one of the things in this class that you want to be careful of, is that you're always looking, especially when we work with equations, that you're always asking yourself, like, what type of equation is this? Because we have different techniques for each type, and it can be easy to just jump right in and like kind of go on autopilot without like deliberately thinking about what it is you're actually trying to do. So slowing down for a minute and asking yourself what type of equation you're working with is always helpful. So today we're just going to work with linear equations. So linear equations, the quick way of saying it is that linear equations means that there are no exponents other than 1 on the variable. So it turns out that that means a lot of things. It means that it can't have like an x squared in it, which is sort of the obvious case, or x to the third, or x to the fourth, or x to the fifth. However, it also means that the variable cannot be under a radical. So like the square root of x plus 6 equals 9. That doesn't look like there is an exponent on the variable, but it turns out that the square root is really an exponent of 1/2. So when we have a square root over a variable, that really counts as having an exponent. And you don't have to know that right now, like what the exponent is. You just have to know that if there's a radical over the variable, then it's not going to be linear. And also, if your variable is in the denominator of a fraction, it is not linear. Again, that doesn't look like there's exponents, but we will learn next week that a negative exponent brings a variable down into the denominator. So if I have like 1 over x plus 9 equals 8, that's the same as x to the negative 1 plus 9 equals 8. And then all of a sudden we can see that we have an exponent other than 1. So it seems pretty simple to just look for exponents, but they're kind of hidden in some places because there's different ways of writing expressions that are exponential. So in general, all linear equations in one variable can be simplified to the form ax plus b equals cx plus d. If you distribute to get rid of all your parentheses, and you combine all your like terms on either side of the equation, then because there's no x squared or x to the third or x to the fourth, at most you're going to have two terms on each side. You're going to have a term containing the variable, so that's your variable term, and a term not containing the variable, so that's a constant term. So we call this guy the variable term. And this guy is the constant term. Yes. In general, a negative exponent means do the opposite of what a positive exponent tells you to do. So if x squared says to multiply by 2 factors of x, then x to the negative 2 says to divide by 2 factors of x. And so that's why it ends up in the denominator. But we'll talk a ton more about that next week. Okay, so we've got linear down. As far as one variable, that just means that there's only an x or a y or an a or a b. There's not an x and a y. So the variable can show up multiple times. So we can have x in the equation several different times, but we don't have a different variable. So there's only one variable in the sense that all of the variable terms contain the same variable. So let's talk about steps for solving. This will probably be review. I encourage you to write the steps down anyway, because they're going to come in really handy when we start doing literal equations in about an hour, which are equations that don't have any numbers in them at all. And it becomes, even though these you've done so many of, like solving when there's numbers, in the equation solving for x, you've probably done so many that you can kind of just do it automatically. Having the steps down for when we get to the harder ones is important, so you can look back and remind yourself of what to do. So the first step is always to clear fractions. By multiplying both sides of the equation by the LCM of all denominators. So over 1. So when I multiply by the LCM, I'm not trying to get common denominators. I'm not trying to make all the denominators the same. I'm multiplying by the LCM over 1 on both sides. I'm allowed to do that in an equation because we have both sides, so we can balance it out by doing it on both sides. So yesterday we worked with expressions. We can kind of think of expressions versus equations in terms of like two different types of scales. So like there's like a bathroom scale, right? When you go in your bathroom, you step on the scale, it tells you a value, and it's not comparing your weight to anything, it's just telling you how much you weigh. That's like an expression. If we were to double you, if you could, you stood on the bathroom scale and doubled yourself, doubled your weight, then the number that it gives you, the value of that weight, is completely different, right? So what we did yesterday when we added and subtracted was we got common denominators so that we were writing the same values in a different way. But we can't just multiply by the LCM because that would be like doubling our weight. Equations, on the other hand, are like those scales that you used in science class. Like, I don't know if you guys did. It was my favorite day in science class when we got to use the scales and the little weights. So all they do is there's two sides, and neither side tells you how much anything weighs. There's no numbers. It just tells you if the two sides are even or not. So if they weigh the same amount, that's like an equation. An equation is just telling you that both sides are equal to one another. So you can do anything you want on one side as long as you change the weight in exactly the same way on the other side to keep it balanced. So the value of each side of the equation isn't important. What's important is that you're keeping that equation balanced by doing the same operation on both sides. So we're just choosing a number to multiply by that's going to cancel off all our fractions, and that number happens to be the LCM. The second step is to simplify each side. Of the equation separately. Sepa. It's an A. Sep. Okay, I got it right. Sorry, I'm like thinking about how you spell separately. By distributing and combining like terms. So at this point, in this step, we don't care that what we're working with happens to be an equation. We're simplifying each side separately, just like we did the expressions yesterday. So notice when I wrote my equation here, each side is an expression on its own, right? So we can do exactly what we did yesterday, simplify using order of operations, and we will end up with an equation in this form. Next, we get all terms containing the variable, so all variable terms on one side. And then all constant terms on the other. The only operations you're allowed to use here are addition and subtraction. So in this whole process, the only time you multiply is in the first step, and the only time you divide is in the last step. When we're moving terms are things that are added and subtracted. So if I want to move terms, I have to use addition and subtraction to move them from one side to the other. And then the last step is to divide both sides. By the coefficient of the variable. The coefficient is the numerical factor within that variable term. So in this case, the coefficient of x is a. Over here, the coefficient of x is c. So it's what your variable is being multiplied by. Any questions about the steps in general before we do some examples? Good stuff? Okay, let's do a few. Let's solve. I need lined paper. I can't write straight to save my life. Here we go. Yeah, it's better. Let's start with we should just start with a fraction one. Let's do 2/3 x minus 4 equals 4x plus 1/2. So first things first, I see that there's fractions in the equation. I want to get rid of them because they're no fun to work with. And this whole process of clearing fractions is important. It is true that we could solve this equation without clearing fractions. Like, we could add or subtract 2/3 x from both sides and like do the calculation 4 minus 2/3, and same thing with the 1/2. However, when we start getting into equations that do have variables in the denominator that are not linear, so we call those rational equations, we have to clear the fractions in order to isolate the variable, because in order to get the variable alone, you got to get it up out of that denominator. And so this skill of clearing fractions in an equation is going to be helpful for other types of equations, even though it's not 100% necessary here. I think that even a lot of people are more used to doing it without clearing fractions often, and are a little hesitant to try it this way, but I promise, like, it actually makes life so much easier and so much simpler. Once you get the hang of it, it just takes a little bit of practice. So let's start with finding the LCM. Well, the LCM of 3 and 2 is just 6, right? They don't have any shared factors, so we can just multiply them. So I'm going to multiply both sides of the equation by 6 over 1. So remember, it's the LCM over 1 because you're actually multiplying by the number 6. We are not trying to make the denominator 6. So when I multiply both sides, I'm multiplying the entire left side and the entire right side, which means I have to distribute. I usually skip the step where I write them in parentheses and write the 6 out front and just go ahead and multiply it by each term. So, yes?
Why 6 over 1 and why not like 3 over 1?
So the reason I chose 6 is because it's going to cancel both of my denominators.
Oh, both fractions.
Yeah.
Okay, gotcha.
So we have 6 over 1 times 2/3 x minus 6 over 1 times 4 equals 6 over 1 times 4x plus 6 over 1 times 1/2. It can be tempting to only multiply 6 by the fractions because that's what we're trying to get rid of. But remember that the reason we're allowed to multiply everything by 6 is because we're keeping it balanced on both sides. So that means that I have to make everything in the fraction 6 times as big. I can't just do it to the fractions.
Wouldn't you put a 1 under the 4 and the 4x?
Oh, sure, if you want to.
Oh,
I mean, in reality, I would probably just write this as 6.
okay.
It's a little less to do. I wanted to make it look the same throughout, but you're really just multiplying by 6. The only reason we put it over 1 when we have fractions is just so that everything's on the same level and we don't accidentally multiply by 6 in the denominator. So then when we do this multiplication, you can do what we did yesterday and do prime factorization and cancel all the common factors. But the way we've set it up, we know that all the denominators are going to cancel because what we multiplied by is a multiple of all the denominators, which means that each denominator divides evenly into 6. So we can think of this as 6 divided by 3 times 2. So like I can rewrite this fraction like that if I want. Right?
So what you're saying is just cross out the 3, put a 1, and see how many times 3 goes into 2. Replace it with a 2. 2 times 2 is 4.
Yep. 6 divided by 3 is 2 times 2 is 4. So the reason we can do that is that remember that 6 over 1 times 2 over 3 is 6 times 2 over 1 times 3. And so I'm just rearranging. I'm just saying I'm going to do 6 divided by 3 times 2 over 1 instead. And we can do that because just like yesterday, we took all the factors and we put them in one big fraction, right? So we're just making a single fraction out of this. Mike, you look unhappy about this.
Yeah, I don't understand where the 1/2. Normally what we did is 2 times 3 over 6 because that's what 2 times 3 is 6, then you cancel.
Yes, and you can certainly do that. So you can do 2 times 3 times 2 over 3. Whoa, that's supposed to be a 3. And cancel the 3, and that's fine.
Okay.
If you're more comfortable with that, definitely do that. As these get a little bit more tedious or a little bit more complex, and there's more factors we're dealing with, it can get a little bit tedious to do that.
So you just took the 1 from the 6 and made it 2 over 1 then? Is that how?
Yeah, so I said that this is 6 times 2 over 1 times 3.
Oh, because the 3 is...
Right, so just like we did yesterday, we just smushed the two fractions together. And then I said, I'm just going to call this 3 times 1 instead of 1 times 3. And so I have 6 divided by 3 times 2. Which I would never expect you to write out. Like, the whole point of doing it that way is that you can do it in your head. So if you're going to write it out, you might as well write out prime factorization and just do it that way. But once you get the hang of it, it goes pretty quick. So we divide the LCM by the denominator and then multiply by the factor in the numerator. And you can definitely write it to help keep track if it helps. So 4x 24 equals 24x plus 3. The slash and dash that I just did there is not good notation when you're doing problems like the ones we were doing yesterday. Like when we're just multiplying a bunch of fractions and we have a bunch of factors to cancel. The only reason it's fine here is because we know that the entire denominator is going to cancel, right? So because we're dividing that LCM by the denominator, we end up with one factor and one factor only when we slash that LCM out. So we're not like, I won't even go there. I see some crazy stuff. It gets really, really messy if like you have a lot of factors and you cancel one and write one and then cancel something from there and write. It just gets pretty crazy. But here, because you can do it all in one step, it's fine to just slash that out and write the leftover factor. So now where are we? Oh, we are simplifying both sides individually by distributing and combining like terms. There's nothing to do here. The left side is fully simplified. The right side is fully simplified. We know this because we have exactly 2 terms on each side, one constant term and one variable term. So I'm going to get the variable terms on one side. Which side you choose is totally up to you. Some people really like their variable to be on the left, which is fine. It actually will come in handy when we start solving inequalities to have your variable on the left. So I am one of those people. I always get my variable terms on the left. Some people would rather have positive coefficients, and so they do whatever they have to make it positive. It's totally fine. What do you guys want to do? Do you guys want to subtract 24x first, or do you want to subtract 4x first?
I'm a lefter.
I'm a lefter as well. So let's subtract 24x from both sides. 4x minus 24x is negative 20x. And 24x minus 24x is 0, plus 3 is 3. So if you're coming from 065, you probably wrote the minus 24x. You don't need to write it anymore. But you still need to think it. Like, you know, like actually, like just like I said out loud, I said 4x minus 24x is negative 20x, right? Like, so you want to think through it to make sure that you're doing the operations correctly. But we don't have to write them anymore. As we get into different types of equations, there's going to be enough steps without having to write all the addition, subtraction, multiplication, division. Next, we are going to add 24 to both sides to get my constant terms on the right. So when I add 24 to the left side, I'm left with negative 20x. 3 plus 24 is 27. And next, we will divide both sides by negative 20. Negative 20x divided by negative 20 is just x, and then we have 27 over negative 20, which gives us negative 27/20ths. And that's done because it can't be simplified. Like, so If you're not sure if that can be simplified or not, go ahead and do the prime factorization. I know that 27 only has factors of 3. It's 3 times 3 times 3. And 20 doesn't have a factor of 3, and that's why I didn't bother doing the factorization, because I know they don't have anything in common. There is no need to write this as a mixed number. Improper fractions are totally proper mathematically. The reason they're called improper fractions, I did not learn this, by the way, until like 5 years ago. Like, my entire mathematical career, I thought improper fractions were called improper fractions because something mathematically, like, somebody thought they were improper mathematically. Turns out they're not called improper fractions because they're mathematically improper. It's because it's bad English. It's improper English to say, I'm going to go to the store and buy 3/2 of a foot of rope. It's proper English to say I'm going to go to the store and buy 1.5 feet of rope, right? So that's why they're called improper. It doesn't have anything to do with the math. In fact, it's a lot easier to work with improper fractions than mixed numbers. In addition, have you ever wondered about this? In algebra, when we smush two things together without an operation between them, what operation is implied there between the 4 and the x? When I smush that 4 and that 2/3 together, what operation is it? It's a mixed number. That operation is addition. This means 4 plus 2/3. It's the only place in mathematics where we smush two things together and it's really addition rather than multiplication. So again, it's just not super consistent with all the other rules we use in algebra, and so we just don't bother with mixed numbers at all, which saves you a step.
You use multiplication and addition to turn it back to an improper fraction, right?
Yes. But I can't remember what I wrote 4 2/3. But it's not multiplication in the sense that you're multiplying 4 times 2/3. It's multiplication in the sense that you are multiplying 4/1 times 3/3 and adding that to 2/3. So you get common denominators. Just like we did yesterday when, I'm sorry, that watermark is not on my screen, so I always forget about it. If I write in that corner and you can't see what I'm writing, please feel free to speak up. I try to remember. Okay, we feel good about this? Is this all review? We've all seen solving equations before. Okay. So there are a couple special types of equations that don't have just one solution. So when we solve linear equations, there's 3 possibilities. And we will do more examples. I'm just going to stop, but I want to show you these first, so we can do some of these too. 4 solutions to linear equations. The first possibility is that there is one solution. When there's one solution, this is what we're typically used to. We isolate the variable on one side, we get a constant on the other side, and that constant is our solution. So we end up with x equals a number. And that number is your single solution. It's the only number that the variable can be replaced with that will make the equation true. That's what it means to be the solution of an equation. Another possibility is that there is no solution. So we call this a contradiction, and probably the simplest example is x equals x plus 1. That says I have some number and I want it to be equal to 1 more than itself. That's impossible, right? That would be like 2 equals 3, 3 equals 4, 4 equals 5, 5 equals 6. There's no number I can put in there that will make a number equal to 1 more than itself. It's just impossible. The right side is always going to be 1 more than the left side, no matter what I do. Well, let's see what happens when we try to solve this. Well, we would say, okay, I need to get the variable terms on the left side because the constant's on the right. So I would subtract x from both sides. What do you get when you subtract x from the left side? You get 0. And what do you get when you subtract x from the right side?
We're taking x from both sides.
Mm-hmm.
1.
Yes, we just get 1 because x minus x is 0 again. And we get something that's just not true, ever.
Equal 1.
Right, 0 is never equal to 1. So that's what's going to happen when you have an equation that has no solution, is you'll end up losing all of your variable terms, and you'll have a number equals some other number. So you end up with, this is what we call a contradiction. It's an equation that's never true. So we say there is no solution.
When would you take x from both sides? I mean, normally, don't you just take it from one side and transport it over? So when would you take them from both sides?
So we always take it from both sides. So when we did this step, we subtracted 24x from both sides. We did 4x minus 24x minus 24 equals 24x minus 24x plus 3. And this happens to be 0. And so that's how we end up with a 3 on the right.
I'm confused. I only see 124x.
So there's one right here.
Okay, yeah, I'm talking about there. Like normally, you would just take 1x from one side, minus 4x to the 24x, or minus the 24x underneath the 4x. But I don't see two 24x's up there.
So
I see you would add 24, put it over to the 3, minus 24, put it over to the 4. The x's are like by them isolated, and the non-variables are isolated.
you're saying we should get this, right? Is there a next step? When we subtract 24x?
And then the 4x.
Okay, so let's pause here. How did this guy go from 24x plus 3 to 3?
You just took away the 24x and put it underneath the 4x to combine the two.
So I took away 24x from both sides. So moving things isn't actually a mathematical operation. What we do is addition, subtraction, multiplication, or division on both sides. So remember, we're keeping the scales even. So if I want that 24x not to be on the right side, then I'm taking 24x pounds off of the right side, and so I'm also going to take 24x pounds off of the left side. So what's really happening here is we're doing 4x minus 24x minus 24 equals 24x minus 24x plus 3. And the reason that we do that is because that gives me 0 here, which is what we want. We don't want that variable over there. And then over here, so it's common to focus on the numbers. So the thing that actually, like where you do the calculation, that negative 20x. The reality is we subtracted 24x because we decided we didn't want that 24x on the right side. And the fact that we ended up with negative 20x on the left is just a byproduct of us getting rid of it on the right side. So we subtracted it from the right side to get just 3, and then had to repeat the same operation on the left side to keep it balanced.
So it's just an imaginary, well, it's like an invisible number then, basically. So because it's there, but you can't see it. You just have to expect it to be there. So just say you were taking away 4x from this side.
From both sides.
Yeah. So then 4x would be on the other side as well, even though you can't see it.
So we start, whoa, sorry. That's supposed to be an eraser. We start here.
Yeah.
That's what we have.
Yeah.
We take 4x from this side, and we take 4x from this side.
Yeah. Okay.
So again, think of the scale, like imagine like actually physically taking 4x pounds from both sides. If we took it just from one side, then it would make it unbalanced. So when we do, we use the term, and maybe I'm a little lazy about it, we use the term moving, when in reality moving things isn't a mathematical operation. The only thing you're actually allowed to do is addition, subtraction, multiplication, division. And we have to do it, the same operation on both sides to keep it even. So the reason that this looks different is just that we don't end up with a term containing the variable on one of the sides. We get a 0 for both of them, and so they both go away. And so it looks like we've done a little bit more, when in reality we did exactly the same thing we did over here.
Could you do an example?
Mm-hmm. Of one with no solution?
Yeah.
Yeah. Let's do it. So let's solve. I have these labeled. Let's do 22x minus 12 equals 5 times 4x plus 3 plus 2x. So again, we're going to start just by simplifying both sides individually. So on the left side, we're all good.
Okay, I see. Okay.
And on the right side, we'll distribute that 5, which gives me 20x plus 15 plus 2x. Then when I combine like terms, we get 22x minus 12 equals 22x plus 15. And at this point, when you see that you have the same coefficient on your variable on both sides, that's when you know something funky is about to happen. Be careful though, because it's not always that there's no solution. There's this third possibility, which we'll talk about in a second. In this case, when I subtract 22x from both sides, I just end up with negative 12 equals 15, which is just not a true statement. If that is never true, then the original equation is never true, and so we say there's no solution. Sorry, this thing's lagging. Come on, buddy.
So you don't have to go through moving the 12 over to the
Nope.
15 at that point to get a 0. 'Cause
No. Once you have a number equals another number,
that's it.
you're done.
And that would be the same if the non-variable numbers equals
Oh.
not equal 0.
Good question. Let's look and see. That is our third possibility. The third possibility is that all real numbers are solutions. So a good example of that would be like 4 times x plus 5 equals 4x plus 20. What I just wrote there, I'm sorry,
You kind of went off the edge.
got a little less screen than I do. I'll just redo it. So 4 times x plus 5 equals 4x plus 20. I think I drank too much coffee this morning. I'm wobbly. So you probably recognize that as just the distributive property, right? So if we distribute that 4, we get 4x plus 20, and that's going to be true no matter what x is, right? So those two expressions are equal no matter what number I put in for x, which means that I can replace my variable with any real number, and it will make the equation true, which means that all real numbers are solutions.
Real numbers are plus numbers? Or negative?
Real numbers are the only numbers that we will work with, and probably that you've worked with in any other class. That real numbers are all numbers except for those that contain the square root of a negative, which so I bother to say real numbers because when you start working with complex numbers, you'll want to differentiate between equations that have no real solutions and equations that have
Real solution.
you can have no solution at all, you can have no real solution, or you can have a real solution. But there's a difference between not having any solution and not having real solutions, which we don't have to worry about at this point. I don't want you to have to change the way you do this problem later on when we introduce something else, so we say what we mean. So this is what we call an identity. It is always true. Let's see what happens if we try to solve this equation. So it feels a little silly because the first thing we're going to do to solve that equation is what?
Multiply.
Yeah, we have to multiply on the left, right? We'll distribute that 4. And when we do that, we end up with 4x plus 20 equals 4x plus 20, at which point you are more than welcome to say that all real numbers are solutions because both sides are the same. If you didn't notice that at this point, which, I mean, let's be real, when you're taking a test, it's easy to get a little bit anxious and not notice things that seem obvious at other times. So if you didn't notice that both sides are the same and so all real numbers are solutions, you would continue trying to solve and you would subtract 4x from both sides. And then you would get 20 equals 20, which looks a lot like what we got when there was no solution, but what's the difference?
The numbers match up.
Yeah, 20 is equal to 20, right? That's a true statement, whereas 0 equals 1 is a false statement. And so if that statement is always true, the original equation is always true, and that's when we say all real numbers.
You teach this so much better than my last professor. Oh my God.
I'm glad to hear it. Okay, you guys ready to do a few? Okay, let's do one more together, and then I'll give you a couple to try on your own. Because I know there's one like this on your homework, and every summer it gets hairy. So we're going to do one together. We're going to solve 2 times 4 minus 2 times 3 minus x minus 1 equals 4 times 2 times 4x. Sorry, I'm trying to be neat. It's 4x minus 3 plus 7
At least you're doing it like
minus 25. Now, before we even start, after you finish writing it down, just make sure, like, look back and make sure that all of your brackets and parentheses are in the right place. So they didn't jump and get a plus 7 inside the parentheses or anything like that. So this looks like a complex equation, right? We look at it, we're like, oh, that's messy. But in reality, the solving of the equation itself is just as simple as the other equations we've done. It's just a matter of simplifying first. So you want to think of this just like the problems we did yesterday. So the left side is an expression, which we can simplify. The right side is an expression, which we can simplify. So just like we did with those expressions on that back page of yesterday's homework, you're just going to distribute combined like terms from the inside out. So on the left side, we have 4 minus 6 plus 2x. We distributed that negative 2. On the right side, we have 8x minus 6 plus 7 minus 25. So we distributed the 2. Now I'm going to combine like terms inside the brackets before I distribute more. If you do that, it makes your life so much easier. The very last problem on the homework yesterday, If you combine like terms inside each set of grouping symbols first, it was so much simpler. So I'm going to do 4 minus 6, which is negative 2 plus 2x minus 1 equals 4 times 8x plus 1 minus 25.
Oh, that's a bracket.
Which one?
2x.
I'm sorry.
Looks like a 3 says.
Yeah. Note to self, don't drink coffee right before class. Okay. So now we'll distribute again. So be sure that when you distribute that 2, you're only distributing it to the terms that are inside the bracket. So the minus 1 just hangs out. We don't distribute the 2 to the minus 1 because it's not part of what we're multiplying it by. So we end up with negative 4 plus 4x minus 1 equals 32x plus 4 minus 25. And now we'll combine like terms one more time, and then we'll be ready to actually solve for x. So 4x minus 5 equals 32x minus 21. Now we'll get all variable terms on one side, so we'll subtract 32 from both sides. 4x minus 32x is negative 28x. And then over here, I end up with just negative 21. Then we'll add 5 on both sides. So we get negative 28x equals negative 16. Hopefully I did that right, yeah. You know how you guys feel like when you're taking a test, you know, like test anxiety? That's how I feel when I like do these calculations in my head, like in front of everybody. I'm sure half the time I'm going to mess up. So definitely call me out if I do. So lastly, we're going to divide both sides by negative 28. So we get x equals negative 16 divided by negative 28. Well, we can cancel the negatives. There's 2 of them. And then 16 is 4 times 4, and 28 is 4 times 7. So if you know that there's a common factor in the numerator and denominator, it's totally fine to not do the full prime factorization. Just take out the factor that you know is going to cancel. And we get x equals 4/7. Okay. Try these ones. We'll do 2x plus 7 times x minus 4, 13. Oh, we should do one with fractions in it. Okay. So we're going to distribute that 7x first. Do you see it? Okay. Did anybody else get anything other than no solution? We all feel good about that one? I'm happy to do it. I just don't want to bore you if we all already did it correctly. Are we good with the first one? Okay. So on the second one, what'd you guys get?
0. X equals 0.
Yes. Did we all get x equals 0? Anybody? Okay.
X equals 1, 6.
Ooh, let's look. So 22x minus 1 equals 10x minus 5 plus 4. I bet it has to do maybe with this addition right here. So negative 5 plus 4 is going to be a negative 1. So we get 10x minus 1 there.
No, got that.
And then one good tip is to always, so when we wrote our steps, notice that I said to get all the variable terms on one side first, and then all the constant terms on the other. It is not incorrect to do it the other way. So it's not incorrect at this point to add 1 to both sides. However, I find that people sometimes get a little bit discombobulated when they end up with 22x equals 10x. Like, it just looks weird because there's no numbers. And so if you move the variable term first, you won't get in those kind of funny situations where it just looks weird. The same is true when we end up with no solution or all real numbers. If you end up with, if you move your constants first, you're going to have only a variable term on one side, and then when you subtract, you're going to have to remember to put 0 there, which it looks to me like all of you are doing great with getting 0 and not just saying that it goes away when you subtract something from itself, which is great, so that might not be a problem for you. But it can help if you find yourself getting a little bit caught up with 22x equals 10x to just move the variable terms first. So we're going to subtract 10x from both sides, which gives us 12x minus 1 equals negative 1. And then we'll add 1 to both sides. This is where it is, Delaney. Did you get negative 2?
Yeah.
Yeah, okay. So adding 1 to both sides just gives us 12x equals 0. And that's different than no solution because there's a number you can multiply 12 by to get 0, right? If you multiply 12 by 0, you get 0. So this gives us x equals 0, which you can also get by dividing both sides by 12. Okay, how about this last one? What'd you all get there?
The only question I have about that one
Mm-hmm.
is I know you said clear fractions first.
Yes.
I always have the habit of doing the negative 2, negative 2x, and then the negative 2.
Yeah, that's a great point. So there's a couple things we can say about this. One is that because I have to write them in some order, I write the steps in this order. Steps 1 and 2 are completely interchangeable. You can clear fractions first, or you can distribute first. Whatever seems the simplest in the given situation. Where you would want to clear fractions first would be like if you have a fraction here, and then distributing it gets a little bit hairy. But I'm gonna clear fractions first rather than distributing first, just so we can talk about what happens when you multiply everything by 4, because it can be a little tricky, like what you're actually multiplying by 4 here. Remember that we are multiplying every term by 4. Terms are separated by addition and subtraction. So we have 4 terms. So we're doing 4, oh, that was a fraction, 4 over 1 times 5/4 x minus 4 times 2 equals 4 over 1 times 5/2 x minus 4 times 2 times x plus 1. Notice that I didn't multiply 4 by the x plus 1 again, just like I didn't multiply 4 by this x separately from the 5/4, right? Because there's no addition between the 2 and the x plus 1, that's all one term, so we multiply it by 4 once. And when we multiply 3 numbers together, how do you multiply 3 numbers together? It's a hard question to answer because we typically do it really quickly in our heads.
Multiply them together, like 4 times 2 times 3 or whatever you got in succession. Yeah.
What do you do first?
I start left to right.
Yeah, so you do them 2 at a time, right? Like there's actually no way to multiply 3 numbers together all at once, even though it feels like we do it because we do it so quickly. It feels like we're multiplying them all at once, but really we're doing them 2 at a time. So the same is true here. When I multiply 4 by 2 times x plus 1, I'm just going to multiply the first 2 numbers and then multiply that result by the third. So we end up with 5x minus 8 equals, what is this, 10x minus 8 times x plus 1. Because I'm multiplying 3 numbers, 4 times 2 times x plus 1. Those are my 3 numbers. Just like when I do it down here, I would do 2 times 3 first and get 6 times 5. It's exactly the same thing I did there, is I just multiplied the first 2 factors, and now I can just distribute once, and I don't have to distribute twice, which is kind of nice. So we get 5x minus 8 equals 10x minus 8x minus 8. Combine some like terms. Subtract 2x from both sides. Gives me 3x equals 0 and x equals 0 again. Again, on this one, distributing the negative 2 first probably would be the practical thing to do.
So we can do it that way?
Yeah.
Oh, okay.
So the reason I wanted to show you this bit about how it would work if you cleared fractions first is that if this 2 was a fraction rather than a whole number, then it would make more sense to clear fractions before distributing. So it's worth understanding how to do it both ways. Okay, now for the fun stuff. These are going to look different, but they're really the same thing, and that's the key, is remembering that variables just are numbers. So we can treat them the same way we treat numbers. So we are solving literal equations. Oh, red is harsh.
Is this like a over b equals m plus c solve for some heat? Okay.
So again, all we're doing is solving equations that have more than one variable, but we're treating all the variables like constants except the one we're solving for. So for example, let's start with something fairly mundane. I'm going to solve S equals 849 x for x. In these ones, they have to tell you what variable to solve for because there's more than one. And so what we're doing here is we are treating everything except for the x like a constant, so like a number. So s is just some number. I don't know what it is. So how would I solve that equation? Yeah.
You solve for s and then plug in x for s.
So it's already solved for s, right? Because it tells us s equals 849x. Our goal is to get x alone on one side of the
So
equation.
divide 849x over 849.
Yes, we're going to divide both sides by 849. This is where your steps come in really handy because we're doing the same steps. It's just not quite as easy to see, right? Because there's no numbers there. If I look at, here, let's,
S over 849.
copy. We'll keep this guy handy. There we go. It's a little crooked, but oh well. So we're treating everything like a constant except for x. Are all variable terms on one side? They are, because the only variable is x, right? Technically, yes, there are more than one variable, but because we're thinking of solving this just like an equation in one variable, we only think of the variable that we're solving for as the actual variable. So I have a constant on the left side, that's s, and I have a variable term on the right side. And so really, we're just in step 5. We're going to divide both sides by the coefficient of the variable. So on the left, we have s divided by 849. And on the right, we have 849x divided by 849. These cancel, which gives me x alone. And the beauty of these is you don't even have to do any calculations. You know how you guys hate that you don't have a calculator? You don't need it.
Can't be that.
It is. I mean, there will be some that get a little bit more fun. Then, I mean, that's kind of boring, right, so far. Okay.
Well, I don't mind boring, don't get me wrong.
Okay, let's do another one. Trying to find a good spot for this so we have it at our disposal, but it's not like... Okay, I'm just going to have to bite the bullet and erase this. Okay. Come on. Okie dokie. So we are going to solve ax plus by equals c for y. This is something that we will do a ton of when we work with graphing linear equations in two variables, because we're going to put them in slope-intercept form, which means solving for y. So we're going to solve this equation for y, which means to get y by itself, which means we're thinking of y as the only variable. If you get mixed up on these, feel free to actually replace all the variables that aren't the variable you're solving for with numbers. Like this is the same as 3 times 2 plus 5 times y equals 9. Can you solve that? What would you do?
Well, I get the variable, well, in this case, I'd probably just
So
move
I-
the 5 to the right side versus the 5 y to the right side. I mean, the y to the right side, does that make sense?
Or I'll just minus 6 from this side, minus 6 under the 9.
Oh,
5y
yeah.
equals 3.
Yeah,
And then I'll
so
divide 5 by 5, leave y by itself, 5
So you'd have
across
y
sides,
equals
it'd be
Perfect.
3 over 5.
Mhm.
Yeah.
So we are on step 4 at this point because all the variable terms are already on one side. That 5y is on one side. And so the next step is just to subtract 6 from both sides. So this equation, ax plus by equals c, is exactly the same. It's a number plus a number times y equals a number. That's all it is, I promise. So if I'm looking down my list, I'm like, okay, I want to get all constant terms on the side without the variable. Well, I have 2 terms here. Ax is the constant term because it doesn't contain the variable I'm solving for. So I'm going to subtract ax from both sides. That gives me by equals c minus ax. And now we're on step 5, which just says divide both sides by the coefficient of the variable. What's the coefficient of my variable here?
So B. B.
Yep. So we're going to divide both sides by b.
So
We
C.
get y equals c minus ax, all divided by b. And then you just leave it like that. The idea of this is that we're writing a new formula. So it's the same relationship, but it gives a different output. So this is useful in things like let's say, I'm trying to think of something that somebody might actually do. I don't know. You're calculating your let's do this. Let's say you can buy, I always say CDs, but nobody buys CDs anymore. Let's pretend that somebody's going to buy CDs and they're $20 each. So you know that the total cost of your CDs is going to be 20 times the number of CDs that you're buying. Well, what if instead of knowing how many CDs you want to buy and figuring out what the cost is, you know how much money you have to spend and you want to figure out how many CDs you can buy? Well, if we were doing it one time, then we'd be like, oh, I have $100 and I could solve that for X, right? But what if, for some reason, I did this every time I got money? I wanted to figure out how many CDs I could buy with that amount of money. That would be annoying to solve the equation every single time, when instead I could divide both sides by 20 now, put this baby in an Excel spreadsheet, and then start entering how much money I got, and it'll spit out how many CDs I can buy because we put the number of CDs in terms of the cost. So that's why we do this, is so that when you have repeated processes, you don't have to actually solve the equation every single time you plug in a different number for A, X, B, and C. Yes?
I just don't get why you subtracted AX first.
So, so the reason we subtracted AX is because we're doing this step right here. We're getting all the constant terms on the side that the variable is not on. Again, the key is to remember that the only variable is the one you're solving for. So the only variable term I have is by. AX is a constant term because it doesn't contain a y. And so remember when we wrote, like, we had this one, I'm going to get the numbers different, but what's the first thing you would do to solve that equation?
Subtract 6.
Right, that's what subtracting AX is about up here. It's a number plus a number times y, just like down here we have a number plus a number times y equals some other number. So same exact process, same exact steps, It just looks different. Does that answer your question?
So in theory, anything that's with the y,
Mm-hmm.
the y is gonna be the solution, and the b is gonna be the denominator. So if you had a, b, c, d, e, y, it would be a, b, c, d, e as the denominator divided by c minus ax or whatever.
Whatever, yeah. Yeah, you're always dividing by the coefficient of your variable. Okay. I'm only going to make it more complex one more time, I promise. This is the last time.
I like the first one.
We're going to solve ax plus b equals cx for x. Think about your steps. There's no fractions, so I don't have to clear fractions. There's no like terms to combine, so I don't have to combine like terms. Step 3 says to do what?
So you have to move the ax or the c, the x over to the ax.
So we want to get all variable terms on one side of the equation. There are two variable terms here, right? Ax and cx, so I'm going to subtract ax from both sides, which will give me b on the left side and cx minus ax on the right. Now, are my constant terms all on one side?
No, you still got
No,
C
you
and
still
A.
get c and a.
Correct. However, those aren't separate terms. So terms are things that are added and subtracted. Factors are things that are being multiplied. The c and the a are both part of the term cx and ax. So I can't like subtract c from both sides, right? Because it's part of this term.
So wouldn't it be like,
So then it would just be
Divided.
divided by b.
yeah, divided by, well,
So we have to combine like terms,
Ah,
don't we?
yeah.
divided by C A.
So it would be
So-
x2 ca or ca x2.
Well, let's back up for a second. If I had 7 equals 5x minus 3x, and you combine like terms, what do you do to combine like terms? Don't tell me what you get, tell me what you do.
You combine.
How?
It depends. Well, it depends on what it is, like that, for that one, it's subtraction,
Subtract, what do you subtract?
the constant, the number.
Right, we just subtract the coefficient, and subtracting the coefficient gives me a new coefficient, right? So that's what we're really doing. We're saying the thing that's multiplied by x is the difference between my two coefficients. Think about it as undistributing the x. If I were to distribute the x here, I'd get 5x minus 3x, right? So we can do the distributive property backwards as well. So what's the new coefficient going to be here?
CA.
What operation did we do with our coefficients on over here with the numbers?
We just separated them from the X via parentheses.
But we did an operation.
Distributed. Or
To get 2x, what did we do with the 5 and the 3?
we subtracted it.
We subtracted them, right? So we subtracted our coefficients to get our new coefficient. So we're going to subtract our coefficients to get our new coefficient. So what should my new coefficient be?
C minus A.
Mm-hmm. And again, think of it as like undistributing that x. This is what combining like terms actually is it's actually undistributing. We just, when there's numbers involved, it's a lot easier to just do the subtraction than to think of it as the distributive property
So once you get
backwards.
separated, then would you divide CA over B?
You would divide
under
both
B.
sides by the coefficient of x, which is c minus a. Yep. So b over c minus a equals x.
So it's never x squared because you technically have two x's.
So we only get x squared when we multiply x by itself. Just like when we do 5x minus 3x, we don't get 2x squared, right? So the key to all of this is remembering that variables behave exactly like numbers. If I don't get 2x squared over here, then I can't get an x squared over here. Because all I'm doing is I'm replacing that 5 and 3 with c and a. It looks very different. I can't actually do the calculation, which makes me feel uncomfortable maybe, but it behaves exactly the same way. We're doing the same process, and so we're going to end up with the same type of thing. It just, like I said, it looks a little different. Should we do one more like this? I think maybe one more.
Yeah.
I want to know what genius thought it was a good idea to put letters in.
Oh, the genius that didn't want to have to calculate things every single time. I mean, isn't it nicer to have a big formula with a bunch of letters and just plug numbers in than to like derive the formula every single time? Gosh, that would be annoying. You just wait till we derive the quadratic
That's why I
formula.
got a calculator.
I guess.
I get they didn't have calculators back then, but we got them.
Well, it turns out that math actually doesn't have a lot that much to do with numbers.
Yeah.
When we do the math that like they do to like classify the universe and the shape of the universe and stuff like that, it really doesn't have to do with numbers at all. Yeah, it's more theoretical, and so that's why we need variables, because the numbers don't matter that much. Okay, let's do find one. We'll solve 3x equals, oh, this is a good one, 2x over a plus b. What is the first step to solving an equation?
Get rid of the fraction, clear the fraction.
Clear a fraction. So I'm going to multiply both sides by a. So I have a times 3x equals a over 1 times 2x over a. Oh, I didn't write 4x up here, sorry. Plus a times b. So 3ax, pro tip, when you have more than one variable in a single term, put the variables in alphabetical order. That way, when things are like terms, they look like terms, and you don't have like an ax in one place and an xa in another place and think that they're different. Here, my a's just cancel, so we have 2x plus a times b. What next?
Get your variables all on one side.
Yep, we're going to get variable terms on one side. So I see that I have a variable term on the left and on the right. So I'm going to move the one on the right to the left by subtracting 2x. So we have 3ax minus 2x equals ab. And now we're going to combine like terms. We know that our goal is to have some new coefficient times our variable. We get the new coefficient by subtracting the old coefficients. So what's my new coefficient going to be?
3x.
Minus a.
So this guy, the x's are what we're counting.
So yeah, it'll be
So what's the coefficient of x in this term?
3a
Mhm.
minus 2.
There you go, good.
My bad, I thought we were getting at something different.
Equals
Divided by
AB.
Divided by AB.
Yeah.
Well, so,
Now we gotta get the a.
Oh, no, we gotta move this.
yeah. And so x equals AB divided by 3a minus 2. Do not cancel anything. We will talk in much more detail about what you can and cannot cancel. At this point, just don't cancel things when you do these problems. That factor of a cannot be canceled because there's subtraction in the denominator. So the denominator doesn't actually have a single factor of a. But like I said, we'll talk in a lot more detail about that.
Because it's technically like having 3 A's there, right?
Mm-hmm.
So I'm gonna guess we're gonna have one on mine. This always happens. So what if there were 2 x's on both sides? So you had 3ax equals 2, or where did you start this at? I don't remember. So the
Here, I started with the fractional one, but let's back up here because I think we can answer your question without clearing fractions again.
Okay. So yeah, so there was, just say you had 3x equals a or b plus x or something. You had 2 variables on both sides.
Yeah,
So how would we?
that's what we
Just
have.
move the 2x over.
That's what we did. We did that. Do you mean?
Oh, okay. I see. Yeah. Okay.
Are you maybe talking about maybe having
Well,
like?
I remember doing some.
What if I had like a 10z right here?
10z equals, yeah, so there was an additional like constant or coefficient.
Right.
Yeah.
So now we just have a constant term on the left as well as the right. So it's not going to change the process. We have 10z plus 3ax minus 2x equals ab. We got all terms containing the variable on one side. What's the next step?
Combining like terms, but there aren't like terms.
So you.
So-
this is where like, can you stick more than 2 in the parentheses at a time? Like, can you have 3 separate?
This is where remember I told you guys having the steps in front of you is really helpful. Just read through them one by one because you're gonna, like when you go into autopilot and start moving stuff around, I can't tell you how many times I've seen people like just move terms back and forth and back and forth and back and forth on these because you're not super grounded in like what exactly you're trying to accomplish. Because when there's not numbers, when there's all these variables, it can get tricky. So what we just did was we got all variable terms on one side. What is the next step?
Build constants on the other side.
Get all constant terms on the other side. So this 10z doesn't contain an x. So I have to subtract it from both sides. So 3ax minus 2x
Okay, that explains.
equals ab minus 10z.
Okay. Yeah, I didn't know if we would do it like that or if we could stick them all in the parentheses, like when we separated the 3
Right.
minus 2. If we could do more than just 2
We
sets. in
You
one of
could
the
do more than
parentheses.
2 sets. However, you can only do it with terms that contain the x. So the
Oh, okay,
10z,
okay,
we wouldn't have been
okay.
able to incorporate that into the left side because it doesn't contain an x.
Okay.
So why do you put the x on the outside of the parentheses?
So because our goal is to have something times x equals something, so that we can do that last step where we divide by whatever x is being multiplied by. If we have 2 factors of x, then what do we divide by to get x alone, right? So what the parentheses are doing are just combining like terms. They're just saying that I have 3ax's minus 2ax's, so that gives me a total of 3a minus 2x's.
Because if it was on the left, then it would be multiplication or distributing of the parentheses.
Well,
So that's why you can't have it on.
no, you can have it on the left.
You can have it on the left?
Sure. It's the same thing.
Oh, I guess, yeah, it's the same thing, because you distributed 3ax and 2x. Okay, gotcha.
10z all over 3a minus 2. Don't cancel anything. You won't have to cancel anything for these problems in your homework. So just as a general rule, don't cancel anything because you might end up doing it wrong. What now?
What do you mean cancel?
Oh,
It's
like
cross out
saying
the
like,
B's.
yeah.
Oh, okay. Didn't even think
Because of that subtraction, it doesn't work the way it does when it's all multiplication, but we will have many more opportunities to talk about that. I just don't want you guys to get frustrated by trying to simplify and getting them wrong. Okay, again, my best advice for these problems is to have this list in front of you and just go through the steps one by one by one. It helps to ground you, so you like have a goal every time you do something instead of just starting to move things around. And